part of the ideas behind creating the preview exercises is sometimes to review the skills you may have learned earlier that we'll be using today. And sometimes it's a way of introducing you to the kind of the concepts behind what we're going to look at today. So notice the topic for today is inverse functions. We're going to spend 2 days on inverse functions. Unfortunately, it's interrupted by spring break, and it wouldn't have been interrupted if we didn't have the 2 days canceled due to snow and ice. So let's take a look at this first idea. When we see an equation like this, x equals 4y plus 9, we say the equation is solved for x. And one of the skills that you're going to need to do to find inverse functions is that you're going to need to solve an equation for the other variable. So in this case, this equation is solved for x. We want to solve it for y. You're very used to these skills. I'm just going to write the answer. Please let me know if you have anything different or you need me to go over it. Okay, so that's what hopefully you have on your papers. Any questions on that? All right. And this idea here with the, starting with a barefoot and the process you go through to get a shoe on, and then undoing this action is an idea that I've been working with since I started teaching here. And originally I would do something like this in say an 095 class to talk about how you solve an equation. You undo what was done to x with inverse operations. But there's another idea here beside, many of you probably have something like this: untie your shoe, take off your sock, and oops, take off your shoe and then take off your sock. And then notice there's a couple of things going on here. You're ending up in exactly the same place that you started off. And this only happens with inverse operations, done in a particular order. So what's important here is not only did you undo each of these 3 actions, but the order that they're done is very important. So notice you undid the last thing you did. Let's see, how do I say this? The first thing you undid, that kind of sounds grammatically wrong. The first undoing is the undoing of the last thing that happened here. So you tied your shoe, that was your final action. The first undoing has to be this last thing you did. So the order is reversed. So the order here is very important. The order of the inverse operations here is reversed. Okay, and if you think about it, that's exactly what happens when you solve an equation. So not only are each individual actions the inverse of the previous ones, but the order that you do it has been reversed. I went to Comcast yesterday for the first time there in Greenfield, and I was turning in an old box, and I was asking what the order is when you're when I wanted to change over a new modem. I know there's an order for your router and your coaxial and power and all that. She said what's really important is the first thing you do is shut off the power, and then when you put your modem back together, the last thing you do is put on the power. And all I could think of was this activity today that I said, I get it, I understand about reversing the steps in the order. So I think we don't even think about this because we go through these things and it's just part of our like everyday sort of habit. If we take this idea now and we're starting to relate it a little bit to mathematics here. So if I start with the number 2 and I multiply it by 3, I get 6. So we start with 2, we multiply it by 3, we end up with 6. If we now take that result, 6, and divide it by 3, notice just like with the barefoot, we're right back to where we started, to 2. Okay, so this idea of performing a series of operations and then undoing them and coming back to where we started is the kind of the central idea behind inverse operations. And you can also think of this like a round trip. You know, hopefully when you go on a round trip, you start in one place, you go somewhere, you come back to the same place you departed from. So now let's do it with some more algebraic looking things. If we start with x and we decide to subtract 1 from x, we get an expression that looks like this. When we multiply by 3, we get an expression that looks like that. So this is the output. If we want to get back into our function language, this would be the output of our first function. Okay, whatever. So here's our first function. Let's call it f. We started off with x, and what came out was 3 times the quantity x minus 1. This is f of x. Now we're taking the output and we're going to undo it. That sounds just like a composition of functions. I'm taking the output from my first function and I'm going to undo it. And the way I undo it is I undo the last thing I did. The last thing I did here was multiply by 3. So the first thing I'm going to do with that output is divide it by 3. I'm undoing the last thing I did. That now leaves me with x minus 1. And now I'm going to undo the first thing I did. The first thing I did was subtract 1, and now I'm going to add 1. And lo and behold, when I simplify that expression, my 1's cancel on back to x. So now I have this other function. We're now going to call this function f inverse, and that's the way we denote it. When I compose two functions and I come back with the same exact quantity I started with, then what I've done is I have worked with composing two inverse functions. So you'll be introduced to this language in a page and a half, this notation, excuse me, and the language. But I basically wanted to sort of show you where we're heading today. So if I start off with the function f, I take the output and I put it into the inverse machine, the inverse of f. I come right back to where I started. That's what inverse functions are all about. Okay, so, yep, Nick? The first question. You mean number 1? Yeah. Okay.
I realize now I kind of did it. It's kind of ugly, but could it also be
negative x plus 9. It would you? No, I understand. I understand. So you subtracted 4y from both sides, and then you subtracted x from both sides, and then divided by 4. Yeah. Okay. So let's look at how you would determine if these two things are equal. Okay. No? Well, let's see. So the answer is yes, it's okay. And let me just show you how you could decide this for yourself, Nick. Do you agree that I can multiply anything by 1 without changing it? So you could multiply this top by negative 1. But if you multiply the top by negative 1, you must also multiply the bottom. So if I multiply this top by negative 1, the x, the number in front of x, changes to its opposite, and then subtraction of 9 changes to plus, and then the bottom. So yes, that would be just like factoring out negative 1 over negative 1, which is 1. Yeah, they're exactly the same. So it's totally fine. But it's unusual, but it's okay. Yep. Any other questions on these 4 problems before we move along? Okay, so let's take a look at a bit of an application to start to get this idea coming through. So here we have a function, we're going to call it h. H is going to represent the height of a corn seedling over time. The time is measured in days after the seedling's been planted, and we're restricting the domain. Okay, we're restricting the domain. The domain is now 0, starting with 0 and ending with 3 days. So if we were graphing this function, we would have a limited domain, the number of days after planting, 0, 1, 2, 3. And remember that it's all the values in between there as well. And then the vertical axis, your dependent variable, is your height, which measures the height of the seedling in inches. Okay, so to determine the value of h, we say h is a function of time, So you just basically look at your expression and fill in t with each of the input values listed in the t column. And when we do that, we get 6, 8, 10, and 12. So we could plot those 4 points, connect them with a straight line, if we wanted to visually see what was happening. The other thing you could have done is you could have just looked at this equation, and with your knowledge of linear equations and functions, you say, I know I'm starting out at 6 because this is where my function says I'm starting at 6, because when t is 0, that's my starting point. We typically call that the y-intercept. In this case, it would be the h-intercept. I start at 6, and my slope right here tells me what to do as each day passes. My corn seedling grows by 2 inches. So you essentially add 2 to each of your outputs. So depending on where you are, you may have thought of it as just plugging in the values and actually performing these operations, or using the idea behind your linear function. All perfectly legitimate. So let's write the set of ordered pairs for this function, at least described by this table. So my ordered pairs has t for the input and the height. So the number of days is the input, and the height in inches is the output. So I have 0, 6, 1, 8, 2, 10, and 3, 12. So that's the set of 4 ordered pairs. There are 4 solutions for this function. Okay, suppose I wanted to know, right now, when I look at this particular equation, when I say the equation is solved for h, that means if you give me a day, I'll tell you how tall the corn seedling is, okay? You give me a time, I plug it in, and out comes h. What if I want to find how long it takes if my input now is the height of the seedling? What would I do? How would I find that? Solve for t, right. So to answer this question, it would be good to have the equation in the form where we solve for t. You give me a height, I'll give you a day. So to do that, this is like the first preview activity. We want to solve this for t. So we subtract 6 from both sides. And then to get t, I divide by 2. Okay. So now we have t equals h minus 6 divided by 2. So in this case, our input is capital H and our output is the day, number of days. So notice that we've switched the variables. What was the input in our first equation is now the output in our second equation. What was the output in my first equation is now the input in my second equation. So let's create a new table now looking at the values. We've already done this table right here. So let me just right beside this table write those 4 ordered pairs that we just looked at a minute ago: 0, 6, 1, 8, 2, 10, and 3, 12. So those were the ordered pairs for the function h equals f of t. And now let's do the same, perform the same operations or similar operations, but we're going to follow this. H is going to be our input. We're going to subtract 6 and divide by 2. So when the height of the seedling was 6 inches, I know from looking at my graph from above that I should say that what happened on the very first day, but let me just make sure my mathematics support that. There we go. Right. It was 6 inches tall on day 0 when I started to record these measurements. What do you think I would get for when the height is 8 inches? 1, right? 8, 1, 2, and 3, right? So the set of ordered pairs now, this is kind of an interesting thing to see. For this function, the function g, my domain is no longer 0 to 3. My domain is 6 to 12. Those are my inputs. So one of the things to notice here is that the outputs, look at this, the outputs for my first function right here, 6, 8, 10, 12, become the inputs in this second function. So the outputs from my first function, the heights, are now the inputs of my second. So the ordered pairs look like 6, 0, 8, 1, 10, 2, and 12, 3. So let's summarize the observations. Well, we just noticed one observation. So let's see how we would write it. We could say the outputs for the function f are the inputs for the function g. Okay, that's one way we could write it. Another way to write it with our domain and range language. Someone want to help me if I use domain and range language versus outputs and inputs? How I might say the same thing but use the words domain and range. So domain and range are swapped, and let's put it in term let's put it in the appropriate places in this sentence. So we still have function f and g in here. So what would it look like? Right, so that's a new idea. We'll hang on to this in a minute, Mahendra. Let's put that down. So Mahendra said the domain of function f, did you say the domain of function f? Right, is the range of function g. So that would be, let's pick another color right here. Here's f. The domain for f was 0, 1, 2, 3. That's the output, the range of the function g. So we're still working on rewriting this sentence with the words domain and range. Can anybody else help me? Julia? Yep, they are inverses. So right. So you're trying to put it all in one sentence, right? So the domain and range of f become the range and domains of g. Yeah, the inverse, right, of g, range and domain of g. All right. So if I was just taking this sentence, I could cross out outputs for f, which is this green highlight, and put in the word range. The range for the function f, Julia noticed, now becomes the domain for the function g. So the domain and range swap places, and you see that with the ordered pairs, okay? But in general, domain and range swap places. That only happens, if we now go to this notation, that only happens with inverse functions. It's the only time this will happen. And the way we write an inverse function, unfortunately, the notation again can kind of mess students up when they see it for the first time. That has nothing to do with negative exponents. When you see -1 in that kind of place where we usually put an exponent, but there's a function name under it, an italic FGH or a capital FGH type of thing, you read it as F inverse. You don't say F to the -1.
Why wouldn't it just be negative f?
Because opposite means you change sign, and we're talking about
I
inverses.
just mean it's I mean, yeah.
You know, I don't know what the original thinking was of the person who came up with this notation, and I could look into the history of math to see who it was and what century it was, but I don't know I really don't know what was in the back of their mind. But like I say, sometimes it's a little unfortunate because it's not intuitive, but it means F inverse. So they should stick an eye up there, and then we'll think it's an imaginary number. Ah, right? Then we're really in tough shape. So instead of calling it two different letters like this, these two functions right here, this is the height of the seedling, this is the day, given the height. They use this notation. We say that g, this function g, is the inverse of f. That's what we say. Now you could say f is the inverse of g if you wanted. You just pick one of them. All right. No, because then the 2 belongs to both of them. There's not a common, if there was a 2x up here minus 6, then you could cross the 2 out. Yep, just leave it like that. Yep. The only other way you could write this is you could write it as 2 separate fractions like this, or 2 separate terms like that. But you can't just cross the 2 with the 6 because that's not a common factor. Okay. Now,
Say half times x minus 6.
yep, you could say that's another way you could write it. Half times x minus 6. Yep, there's all types of ways. X over 2 minus 3. Yep. Okay. All right. Yeah, I don't think we want to go any further than those 3. Okay. All right. Now notice, I don't think I've ever put in any of your class notes now for the really big idea. So I can't stress enough of how big this idea is, except I'm going to put stars all around this, and you do whatever you need to do on your paper to remind yourself. And this, you're going to see this idea on your next test. You're going to see it on your next, well, you won't have another quiz. You'll see it on your final. You'll see it everywhere, everywhere. I think I'm being silly enough here with the stars. I could throw in a few smiley faces as well. See, if you remember this, you'll be happy. All right. Yep, you better put this on your cheat sheet for sure. All right, so let's go through this and see if we really understand what it's saying. It says that if f and g are 2 functions, okay? Now, again, I want to stress this is a definition. That's a really important idea, that it's a definition. So anytime you want to show that 2 functions are inverses of each other, you must do this. You must do this. And what is it that you must do? Well, first of all, notice you're taking the composition of 2 functions. You're starting out with some input. You're performing the first function on that input. We'll call it our friendly x. You take that output and put it into your next machine called f, and look where you end up with, right back to where you started. That doesn't prove that these are inverse functions just yet. You also have to reverse the order of the composition. Now, if you recall on Monday in class, when we were doing the mother and the father example, the order that you did m of f of p and f of m of p certainly changed the relative we were looking at. And so we said the order of composition is important, and it's not commutative, means that when you reverse the order, you don't get the same result. And I put in front of that in general. This is the only exception to that. When you have functions that are inverses of each other, when you reverse the order of the composition, you still come back to where you started. And it only works when you have inverse functions, only. So instead of now using f and g, this is how we write it. F of f inverse of x is exactly the same as f inverse of f of x. They both bring you back to x. So how would you prove this? Let's look at the 2 functions. You'll have to do this for your class activity. So let's just look at the 2 functions we were looking at a minute ago. We had this function, 6 plus 2x, right? And we were wondering, question mark, if this function, if these were inverses. So if your homework or on a test, I ask you to show that 2 functions are inverses of each other, the only way you can do it is to perform these 2 compositions. And if they both bring you back to x, then you're happy and you can move along. You cannot show it by just putting in individual values like 2 or 3 or 0, because you're only showing it for one number. To show that every possible number in the world satisfies this definition, you have to be general, and that's where the algebra comes in. That's where you use x. So notice we have to show these 2 situations. We have to show that f of g of x is exactly the same as g composed with f of x. We switch the order and both of them bring us back to x. If you show that, then you have inverse functions. And then instead of calling it g of x, you could call it f inverse of x. So let's try it. So what does this say? I'm going to start with x, and I'm going to first put x into my g function. So let's do that. My input into my f function is going to be g of x. And how do I replace g of x in here? How do I replace this green blob? What do I replace it with? With g of x. What's g of x equal? It's sitting right here looking at you. G of x is the same thing as x take away 6 over 2. Okay. So I replace g of x with what it equals. And now my input into the f function is right here. What does my f function tell me to do to any input? Any input into my f function is going to be doubled and then have 6 added to it. So now I'm going to perform this set of this recipe right here to my input. So my input is this yellow blob. So I'm going to take this yellow blob, I'm going to double it, and I'm going to add 6 to it because that's what my f function tells me to do. I double my input, my yellow blob, and I add 6. So now I replace my yellow blob with what it equals, x minus 2. And lo and behold, look what happens. The 2's cancel out. X minus 6 plus 6 brings me back to x. So if I could do a half of a smiley face, that's what I would have right here, half of a smiley face. I can't be confident yet. I've shown the composition brings me back to x by performing it in this order only. Now let me reverse the composition. Let's do g of f of x. And if this comes out to be x, then we're golden. We're all set. So now let's look at the input into our g function. The input into our g function is this green blob called f of x. We know what f of x equals. It's defined right here, 6 plus 2x. So that becomes my green blob. The green blob is 6 plus 2x. Okay, now I look at my g function to see what its set of instructions are for any input. So I go up here and it says g of any input. I take that input, I subtract 6 from it, and I divide it all by 2. So I'm going to take my input, which is this green blob. Here it is. I'm going to do what g tells me to do. I'm going to take that green blob, divide it by 6. Subtract 6 and divide by 2. What's the green blob? Instead of it being called x, it's this thing called f of x, 6 plus 2x. Okay, so let me simplify this. 6 take away 6 plus 2x take away 6 over 2. The 6's cancel, so I get 2x over 2. And lo and behold, I'm back to x. Now I really get to put a smiley face, finish my smiley face. Okay. So anytime you're asked to show that two functions are inverses of each other, this is what you need to do. Whether it's a class activity, a homework problem, or an assessment question on a test, you need to show that if you compose the two functions and then you reverse the composition, the order, they both take you back to x, the original input right here, x. So this is a series of steps you go through. It's the round trip idea. Okay. What's it in front of my x? Right here, 2x divided by 2. Let me see if I can make that hand like that. A little better, Ken? Okay. Yeah. I'll never forget, I was in college and I sent my 4th grade teacher a holiday card. And then I went home for intercession and went to the school and visited her. And she said, Linda, she didn't say like, thanks for the card thing. Because Linda, your penmanship used to be so beautiful. What's happened to it? I'm like, oh my God. So anyway. Yeah, because it's 6 take away 6. That gives you 0. And you got 2x divided by 2. Now you can see, now you can cancel that 2 because it's a factor die. It's multiplying x. So I wanted to say college happened to me. I don't know. I didn't know what to say. All right. Any other questions? Okay, you're all set to start your class activities. Please, I'd like to check before you go on. There's a couple of things I want to check today. One of them is number 3. So please, when you finish number 3, where you have to prove that these two functions are inverses, please ask me to come over and check what you've done. So number 3, I want to check, and I would like to check your language for right here, the inverse right here.